If I hand you these items, a telescope for collecting light from a source, a prism or diffraction grating to split the light, and a recorder for monitoring the intensity at each wavelength, and ask you which chemical species are present in the upper atmosphere of this planet, which is 160 light years away, how would you do it? You can obviously visit the planet to do this. So in today's video, let's learn how we would solve this problem and discuss an exciting paper about it. Let's consider a star which is very similar to our Sun, and let's see how its intensity or amount of energy emitted changes with time with the help of this plot here. Since from numerous missions we have observed that the main sequence stars remain stable for billions of years, the intensity values in the plot shown does not show any major variations. Let's add a planet around the star and see what happens to the graph on the right. We can observe that there are slight dips in the intensity. This is happening because a planet is large enough to block a noticeable portion of the light that is reaching us from the star. These graphs are called transit light curves. Transit because the planet is transiting through our view of the star, and a light curve is basically a graph of the intensity of light versus time. Now let's zoom into the system and observe what is happening with the light from the star. We can see that the majority of the light is unhindered and continues on its path to us, and that's expected due to the size difference between the star and the planet. Some of the light is getting blocked by the surface of the planet, which is causing the dip in the intensity as observed in the previous plot. Some of the light, however, is not getting blocked by the planet but is passing through the atmosphere of the planet. Let's explore the consequences of that. An atmosphere of a planet has multiple chemical species who are not light enough to reach the escape velocity of the planet and hence are gravitational bound to the surface. These species could either be atomic or complex molecules. There are a myriad of ways light can interact with the species. Without explaining all of them and without diving into the complex quantum mechanics involved, I will give a brief explanation about a simple but universal method of interaction between a photon, which is a packet of energy, and an atom. Consider the simplest atom in the universe, the hydrogen atom. It has a proton and an electron. Now, when a photon of certain minimum energy strikes the electron will absorb the energy and get excited according to the rules of quantum mechanics. It's very similar to climbing a staircase where each step has more energy than the previous one. The minimum energy of a photon required to be absorbed is a unique feature of every atom and molecule, just like how each human being has a unique fingerprint. So I hope you are getting a vague understanding of what I am getting at. When a bunch of photons of different energies and hence of different wavelengths, since we know that energy of a photon and its wavelength are directly correlated by this formula here, pass through a collection of atoms or molecules, each atom will absorb the energies characteristics to its electronic structure. Now if we plot the intensity or flux of light received versus the wavelength, we can observe at which wavelengths the photons were absorbed. This is called the absorption spectrum, and the wavelengths at which absorption occurs is unique for each chemical species. Physically, the spectrum is obtained by passing the light collected by a telescope into a prism or a diffraction grating to split the light into its constituent wavelengths. So now I think the picture is clear. When the photons from the host star passes through the atmosphere of the planet, particular wavelengths will be absorbed due to the chemicals present in the atmosphere. The characteristic signatures will present themselves when we observe the spectrum of the star as the planet transits in and out of our line of sight. The spectrum thus produced is called the transmission spectrum. Since we know the exact chemical signature of a huge number of atoms and molecules, we can then identify what is present in the upper layers of the atmosphere. There are a lot of interesting yet complex details involved with this process, which would require a separate video in and of itself. I will not talk about that here, so let's start discussing today's paper. In 2001, this group of scientists reported for the first time about the detection of atomic sodium in the atmosphere of this planet. The lines they observed are a resonance doublet at this wavelength. A doublet state means that the absorption is occurring at two very closely spaced wavelengths, and if not resolved properly, the lines might appear as a single line. If we do the math, then we can calculate the amount of energy that was absorbed by these atoms of sodium present in the atmosphere, whose signature was then observed on Earth. The scientists obtained 684 spectra of the planet from 4 planetary transits using the STIS spectrograph on board the Hubble Space Telescope. Let's take a look at some of the plots. This is a portion of the STIS spectrum of the planet, and you can see a deep absorption in this particular region corresponding to sodium. If you take a look at the y-axis values, you might think that the absorption is not a deep signature. However, in comparison to other absorption bands, it was deep enough to garner some attention. This plot here showcases the entire wavelength range observed. The actual sodium line is here, and the dotted lines here are other strong bands that were considered for comparison purposes. By comparing the transit depth with the other observed bands, they made their conclusion about the detection of sodium. After a rigorous round of analysis, they believed that the observed value of sodium absorption from the planetary atmosphere might have either been a result of a high cloud deck, a low atomic sodium abundance, or a combination of both. I am skipping the data analysis part due to its complexities. However, I would encourage interested readers to check out the paper. The link is given in the description. If you are interested in a discussion, you can post a comment about it and we can engage in a conversation. This is it for today's video. To be honest, there are a lot of interesting parts in the paper, like effective planetary radius and removing limb darkening effects. If you want me to cover the subsequent papers in more detail, or perhaps this paper itself in a greater detail in another video, then please feel free to comment down below. I would be more than happy to do so. I hope you enjoyed the discussion and learned something new. Please like the video and share it with your friends and family. And yes, please subscribe to the channel because your support keeps me going. Thank you, stay curious.